And finally, we have these exercises. I mean, it's just exercise 118, but there are several parts. I1 and I2 are two ideals in the ring A, and J1 and J2 are two ideals in the ring B. And of course, in the background, you know that there is that homomorphism F from A into B. Then we have to prove the following. The first statement is this: the extension of I1 plus I2 is equal to the extension of I1 plus the extension of I2. So we start the solution with this chain of containments. First, we note that f of I1 is contained in f of I1 plus I2, simply because I1 is a subset of I1 plus I2. And f of I1 plus I2 itself is contained in the extension of I1 plus I2, because that's the definition of extension. It is the smallest ideal in the ring B which contains this F image. In a similar manner, f of I2 is also contained in the extension of I1 plus I2. I haven't written that intermediate thing, that is f of I2 is contained in this, which is contained in this. So what do we find? We find that this ideal, this extension which is an ideal in B, contains f of I1 as well as f of I2. So what about the extensions of I1 and I2, the individual extensions, because they are supposed to be the smallest ideals in B containing respectively I1 and I2, and this is just one ideal which contains them. So obviously their extensions would be contained in this, because this is, for example, the smallest ideal in B which contains f of I1. Where is it? Here. And this is some ideal in B containing f of I1. So obviously that smallest nature would imply that this is contained in this. Similarly, this is contained in this, because this by definition is the smallest ideal in B containing f of I2. And this is just some ideal in B containing f of I2. But now you have these two containments. So if you take the sum of these two ideals, then that would also be contained in this. Why? Because this is after all an ideal and hence is closed under the formation of sum. So that's how you have got one of the two containments that you need to conclude equality, namely that this is a subset of this. Now we will prove the reverse inclusion, reverse containment. To prove the reverse inclusion, we start by taking a general element in this extension. And that general element looks like this, that you already know how the elements in the extension of some ideal look. So it is a summation yi times f of mu I plus nu I, where the yi's are coming from our ring B, in which all these things are happening. The mu i's are coming from the first ideal I1 and the nu i's are coming from the second ideal I2. You may think at this stage why we did not have to consider elements to establish the first inclusion. Well, the first inclusion luckily just simply comes like that without having to consider elements. But for the second one we have to consider elements. So what is our aim now? We now want to show that this thing belongs to this sum I1 extension plus I2 extension. And that is absolutely straightforward. So we start with this element and then apply the ring laws to this sum. I have skipped, I think, 2 or 3 steps. Let me tell you what the steps are, although you already know. Because f is a homomorphism, in the first step, you write this f of mu I plus nu I as f of mu I plus f of nu I. And then you multiply that sum by yi, obtaining yi f of mu I plus yi f of nu I. And that is allowed because we have the distributive law in the ring. And then you just simply split the sum into these two sums. What allows you to do so? Namely the facts that addition is both commutative as well as associative. That is why. And now you look at this sum, it has all the things. All the things means it has the form to be an element in I1E. Why? Well, all the yi's already are coming from B, and all these mu i's are in I1. That is why. Similarly, this second sum where all the new i's are coming from I2 belongs to the extension of I2. And that way, any element in I1 plus I2 extension is also present here. So that is why this is also contained in this. Combining this containment and the previous one, you have equality. And the second one involves contraction. The contraction of J1 plus J2 contains, that means has as a subset, the sum of the contractions of J1 and J2. This one is even easier to establish. We just straight away take any element here and it's going to look like this, x plus y, where x belongs to J1 contraction and y belongs to J2 contraction. It is easier because contractions are just inverse images. So J1 contraction is nothing but the inverse image of J1 under F inverse of J1, and J2 contraction is F inverse of J2, that's it. So x belongs to F inverse of J1 means f of x would belong to J1 by the definition of inverse image. So that's how we get this. Similarly, y being in F inverse of J2 means f of y belongs to J2. And then we calculate f value of the sum of x and y. Because f is a homomorphism, so it respects addition, so that is f of x plus f of y. And this belongs to J1 and this belongs to J2, so their sum belongs to the sum of J1 and J2. But then what does that tell us? F of x plus y belongs to this set. So x plus y would belong to the F inverse of that set, which however by definition is just the contraction of J1 plus J2. And that's it. Because any element here is also here. And that is why this is a subset of this. That's the solution. And with this, let me just end this video. There are quite a few other parts in this exercise that we will solve next week. So see you next week with more parts and their solutions. Until then, this is me, Lucifer from A Mathematical Room. Have a nice day.